All right, welcome Algebra 2 students. We are going to jump into Chapter 10, our last unit, and it's going to be about probability. In Section 1, we're going to just talk about some of the foundational stuff we're going to need as we progress through this probability unit. So specifically, we're going to be talking about the fundamental counting principle and permutations. So a permutation is a way of taking a certain amount of objects in ordering them or figuring out how many different ways we can arrange them when order matters. Okay, so let's say for instance I had like two things like X, and they're the same thing but they're different colors. So if we rearranged them, say putting the green first and then the blue last, we'd have two different ways to order these two objects that are essentially the same type of object, but they're unique in that they're different colors. Okay? All right, so a factorial is a symbol, but it means to do a specific operation in math. So specifically, you're going to see this exclamation mark, and that's a factorial. So n factorial means n times n minus 1 times n minus 2 times ... 3 times 2 times 1. Okay? So if we have, say, for example, if we have 4 factorial, what that means is we're going to take 4, and then 4 minus 1, and then 4 minus 2, all the way until we get to 1, and then we multiply them together, so we get 24. Okay? All right, so let's jump in here to the fundamental counting principle. What the fundamental counting principle says is that if we have an event and it can occur a certain amount of times, say m ways, and we have another event that can occur n ways, then the number of ways that both of these events can occur is the product of all the different ways each event can occur. So m times n. So let's apply this in example 1. It says if you have 5 shirts, 3 pairs of pants, 2 pairs of shoes, 3 hats, and 2 coats, how many different outfits can you put together? So what we're going to do is we're going to take 5 times 3 times 2 times 3 times 2, and we're going to multiply those all together, and what we get is 180. Okay? So do we need to buy any school clothes for next year? Well, no, because we have exactly enough to make a distinct outfit for every single day of the school year. All right, let's look at example 2 here. It says, Jason's at Subway and he wants to order a sandwich. But he suddenly realizes that there's so many choices that he gets too overwhelmed and he just decides to order white bread with tuna fish, just something simple. Why does he get overwhelmed? Well, we're going to figure out all the different ways that we can make a unique Subway sandwich with 8 types of bread, 7 types of meat, 8 veggie choices, 5 different cheeses, 6 sauces, and in addition, you can have your sub toasted or not toasted. So using the fundamental counting principle, we're going to say 8 times 7 times 8 times 5 times 6, and then for toasted or not toasted, times 2. So what we get when we multiply that all together is 26,880 types of sandwiches. That's a lot, and I think there's even more choices than what's listed there at Subway itself. So let's see. Let's look at example 3. It says, how many different non-personalized license plates are possible if the first 3 characters have to be letters and the last 3 characters are numbers? So let's say here's our license plate, and the first 3 characters are going to be letters, and then the last 3 are going to be numbers. So for letters, we have 26 choices. That's the letters A to Z, right? For numbers, we have 10 choices. Those are going to be the single digits 0 to 9. So using the fundamental counting principle, for the first letter, we have 26 choices, the second letter, 26, and the third letter, 26. We're multiplying those together. Now, followed by 3 characters, which are numbers, so times 10 times 10 and times 10. Okay? When we multiply these all together, we get 17,576,000, and that's not even including the personalized plates. All right, let's say we have 8 high schools in the Cook Inlet Conference, and we want to figure out how many different ways can these 8 teams finish in the regional track meet. So let's say we just outline here our 8 different high school, 1, 2, 3, 4, 5, 6, 7, 8. Our eight finishers. So first, second, third, dot, dot, dot. This is going to be 8th place. Okay? So we're going to choose someone to finish first. We have 8 choices. Once we've used one up, now we have 7 choices. Okay, if we've used 2 up, we now have 6 choices, followed by 5, 4, 3, 2, and 1. So this is the same thing as saying 8 factorial. Okay, so when we multiply this all out, we get 40,320 different ways the 8 high schools can finish. Now if we consider, well, what are the different ways we can just assign first, second, and third place? So if we just look at first, second, and third place, does that change our answer? Okay, so there's 8 possibilities for first place, right? There's 7 possibilities for second place, and then 6 possibilities for third place. So what we get here is 336. So what we're going to look at next is kind of a quick way to do this same problem using what we talked about earlier, a permutation. So a permutation is taking a set of objects, n, and ordering it r ways. Okay? So applying this last example, so if we use this last example, we have 8 high schools, and we want to figure out how many different ways can we assign first, second, and third place. So we want to order, 3 things. So we're going to use the formula, and it's going to be 8 factorial over 8 minus 3 factorial. So when we simplify this, we of course simplify the bottom first. And then for the top, what we're going to do is we're going to write out the product, but we're going to stop at 5. And the reason why is because now we can cancel out the 5 factorial, and that leaves us with 8 times 7 times 6, which is 336. And that's the same thing we got up here. Okay? All right, so let's apply this. Let's see here. There's a couple typos in here. Let me just fix this real quick. This guy is supposed to be a 6. All right. Okay, so it says 6 students are running the mile, but you can only award prizes to the top 3 finishers. In how many ways can we do that? Okay, so we have 6 things, and we want to order it 3 ways. First, second, and third place prizes. So what that is 6 factorial over 6 minus 3 factorial. So we have 6 factorial over 3 factorial, and now we're going to write the numerator 6 times 5 times 4 times 3 factorial, stopping at 3 factorial, okay, canceling those out, and now we're looking at 6 times 5 times 4, which gives us a total of 120, okay? All right, next example, it says how many different 7-digit telephone numbers are possible if we can repeat digits or if we can't repeat digits. So, kind of like the license plate example, here's our 7-digit telephone number with repeats. Okay? So with repeats, we have 10 digits total, right? 10 total, which is 0 through 9. So it's going to be 10 times 10 times 10 times 10 times 10 times 10 times 10, or 10 to the 7th power, which gives us 10, let's see, 1, 2, 3, 4, 5, 6, 7 zeros. So that gives us 10 million. Now, if we look at without repeats, if we cannot repeat, so no repeats, how does that change our answer? Okay, so this now is like a permutation. So we can say 10, but we can't repeat. So now for our second digit, it's 9, followed by 8 times 7 times 6 times 5 times 4. Or what we can do instead is we can say 10 objects ordered. Now we have 7 digits, right? So 7 ways, a 7-digit phone number. So we can, let me just kind of get rid of this stuff. So what we can do is we can now use our formula, 10 factorial over 10 minus 7 factorial, which is 10 factorial over 3 factorial. And then we could just simplify that, and what we get out is 604,800. Okay, so when we omit those repeats, it reduces our set quite a bit. All right, so 7 says it says you need to assign the roles of president, vice president, and secretary to student body, and preliminary student government elections have determined that you have a subcommittee of 12 students to elect from. So we want to take the 12 students and we want to choose 3 of them to be president, vice president, and secretary. So using our permutation formula, 12 factorial over 12 minus 3 factorial. So that's going to give us 12 factorial over 9 factorial. And again, we're going to write this out, 12 times 11 times 10 times 9 factorial, stopping at 9 so that we can cancel out, and then multiplying 12 times 11 times 10, which gives us 1,320 ways. Okay? Now, we're going to look at this lastly here if we have things that repeat, okay? So permutations with repetition follow a slightly different formula. So say, for instance, I have the word to, this word T-O-O, okay? How many different distinct words can I make with this word to, using these same letters? So I could say T-O-O, I could say maybe O-T-O, so oat, or I could say like O-O-T, so oot, okay? So those are all the different ways. There's 3. So what this means is we have 3 letters, so N equals 3, and we have O, the letter O, it's repeating twice. So S1 equals 2. So applying the formula, it would be 3 factorial over 2 factorial, which would then give us 3, which is our 3 different distinct outcomes. So let's apply this here now to the word tomorrow and yesterday, and we're going to figure out how many different distinct words can we make. So using the word tomorrow, so for tomorrow, we have, let's see, 1, 2, 3, 4, 5, 6, 7, 8 letters, so N equals 8. We have the letter O repeating 3 times. Okay, so O is repeating 3 times, so that's S1 equals 3. And then the letter R repeats 2 times, so S2 equals 2. Okay? So then the formula is going to look like 8 factorial, let's see if this is going to let me write this, 8 factorial over 3 factorial, 2 factorial. Okay? So when we compute that, what we get is 3,360. All right? Now what I want you to do is I want you to try calculating the number of permutations for the word yesterday using this same formula. And then check your work, and what you should get out for the word yesterday is you should get out a total of 90,720. Okay? All right, I hope these video notes helped, and we'll see you next time.